Welcome to the second PowerPoint in the carbonyls topic, so part 2, and we're looking at the reactions of carbonyls. The textbook page references are 457 to 459, and we're on page 5 in your notes. Remember, the chemical reactions of a compound are determined by the functional groups present, so the functional group determines the chemical reactions of the compounds. Now, for the functional group alkene, a C double bond C, the type of reaction they will undergo, hopefully you remembered, electrophilic addition. An electrophile, remember, is a species that accepts a pair of electrons. Those electrons can come from the pi bond. The pi bond is weaker, so it can break easily or more easily. And addition because you will add two different atoms or groups onto each C from that C double bond C. So the name of the mechanism is kind of describing what's happening. So do make sure you're happy with your Year 12 mechanisms, because we're going to teach you a new one now. Because for the carbonyl, it won't actually do the same. Even though there's a double bond there is a difference, remember. The double bond for the alkene, it's between two carbon atoms, so that bond is not polar. There's no permanent dipole there because it's between two atoms of the same type. Whereas with the carbonyl compound, it is polar. If you remember, we drew it out in the first PowerPoint, the C double bond O, there is a permanent dipole there. And that's because the oxygen is more electronegative than carbon. So we can show that in a diagram. I'll just pause there so you can make a note and complete your notes. So we've got two features here to this bond. We've got a permanent dipole due to the fact that the oxygen is more electronegative than carbon. In other words, it has a greater ability to attract a pair of electrons towards itself from the covalent bond. So we've got the permanent dipole, the slightly positive carbon, slightly negative oxygen, but we've also got that double bond as well. So we've got two features here. And it's actually the permanent dipole that kicks the story off. So remember, the mechanism is telling you the story of how they actually react. So the mechanism is going to begin with that permanent dipole. Now, we've seen a mechanism that starts with a dipole before in Year 12, where we've had a permanent dipole to begin with. Can you remember what the functional group was in that situation? Hopefully you're thinking of the haloalkane. So for example here, carbon chlorine. Yeah, the chlorine is more electronegative than the carbon, so it follows that same argument as the CO bond. Okay, so we've got a slightly positive carbon. So can you remember in our haloalkane mechanism, what was the attacking species? What thing would the slightly positive carbon attract? What would we say there? So hopefully you were thinking of a nucleophile. So in the haloalkane, for example, we had the hydroxide ion attacking, and that's because there was a lone pair of electrons on the oxygen that could be then used to form a new covalent bond between the C and the O, and then the carbon-chlorine bond would break. So we had heterolytic bond fission of the carbon-chlorine bond, and the chlorine then was lost. It was substituted. It was kicked out as a chloride ion. Okay, so here, if we have a nucleophile attacking our slightly positive carbon of the carbonyl bond, would we substitute the oxygen, or could we just add something to both atoms? So it would also be an addition reaction. So look, the haloalkane was a nucleophilic substitution reaction because the chlorine, that carbon-chlorine bond broke and the chlorine had to leave. Whereas here, we can break the pi bond between the carbon and the oxygen. So the oxygen still kind of hangs on in there, attached by a sigma bond. So we're not actually substituting anything. It's going to be an addition reaction. So the name of this mechanism then is nucleophilic addition. Okay, so the first bond will be made due to the action of the nucleophile, and we're going to be adding things together. Nothing is going to be substituted here. So it's an addition reaction, nucleophilic addition. So we have a new mechanism to learn. Woohoo, exciting times. So nucleophilic addition. So we're going to get to grips with that in a moment. Before we do though, it's a good opportunity here to just take stock. There are 5 mechanisms that you need to know in A-level chemistry. We've already learnt 3 of them. This is going to be our 4th, and the 5th one is coming up soon in module 6. So let's just take a moment to summarise, to scoop them all together so that we can see which mechanism happens for which type of functional group. Now, the first one we learnt about, of course, was radical substitution. So a radical is a species with an unpaired electron, and we show that with a dot. And this mechanism involves 3 steps, and there isn't a curly arrow in sight. You don't need the curly arrows. It's just equations with dots: initiation, propagation, termination. And the conditions were UV radiation. And the bond fission was homolytic bond fission. So all these key bits of facts there you need to have solid in your mind. Radical substitution. Now that will only happen with alkanes. Okay. So the radical will have come from a halogen. So we convert the alkanes into a haloalkane. Now once we've got our haloalkane, we can change those, and we can do that via nucleophilic substitution. So we've just referred to our haloalkanes because they have a carbon-halogen bond which is polar. So the partially positive carbon will be attacked by a nucleophile, and a nucleophile is attracted to the partially positive carbon, and it will donate a pair of electrons. So a nucleophile is a species that can donate a pair of electrons. So a curly arrow can show the movement of that pair of electrons, and the curly arrow would go from that pair of electrons to the partially positive carbon, because that's what it's going to join to. Now carbon can't have 5 bonds, so the carbon-halogen bond breaks, so the chlorine, for example, or the halogen atom is kicked out, and it gets to take its the electron with it from the covalent bond, the shared pair. So it leaves as a halide ion. So it's a substitution reaction. You are kicking something out, nucleophilic substitution. The third mechanism then at year 12 was electrophilic addition. We've mentioned that again already. An electrophile is an electron pair acceptor. So the curly arrow would come towards it because the movement of the pair of electrons will be going towards the electrophile. And it's addition because the functional group that does this is an alkene. So the pi bond will break, but the sigma bond stays intact. So nothing is kicked out. The carbon is still bonded. So addition because you're adding 2 things together to make a product. Nothing is substituted. And it's the same with our new mechanism now. So you'll see when we start to draw this one out. Okay, it's our aldehyde and ketone. It's our carbonyl compound. So the fact that we have a permanent dipole, the partially positive carbon, is attacked by a nucleophile. The nucleophile donates a pair of electrons to form a new covalent bond between itself and that carbon. So the pi bond between the carbon and the oxygen is going to break. So the oxygen will still be bonded to the carbon, so it's not substituted. It's going to be an addition reaction, so nucleophilic addition. So make sure you've got the definition for a nucleophile and the definition for an electrophile really clear in your mind so that you can write it down if asked, but also so you can apply that knowledge when you're answering exam questions. What's the fifth mechanism going to be called? Have a look. What combination have we not done? So electrophilic substitution is our fifth one. Okay, and we'll reveal which functional group that will be soon enough. Okay, but you can see by that list it could potentially be quite confusing. And if you try to just rote learn it without understanding it, you're going to run the risk of getting confused. So you've really got to make sure that you understand these mechanisms, how they work, what the definitions of an electrophile and a nucleophile are, okay, and remember what type of functional group the mechanism applies to and why. And if you can really get that in your mind and let it get under your skin, then you will be a proper A-level chemist. Okay, so really make sure you're understanding these mechanisms. We'll have a look at our new mechanism shortly. So nucleophilic addition is our new mechanism for carbonyl compounds. Remember, carbonyl compounds are either aldehydes or ketones. Let's just capture a key idea to set the context for this new reaction. We'll do this on a back page. If we take an aldehyde as our example here, remember we make the aldehyde from a primary alcohol, and that's an oxidation reaction. And we do that using distillation to provide the heat for the reaction and to prevent the aldehyde from oxidizing further into a carboxylic acid. The oxidizing agent is potassium dichromate with the conc H2SO4, and we can represent that using O in square brackets. Now, oxidation is the addition of oxygen and or the removal of hydrogen. So if we take an example here, just to have a look, the primary alcohol here is ethanol, so C2H6O. If we play spot the difference, on the right hand side our product, so CHO is the functional group for the aldehyde, so it's ethanol, hence in al, it's C2H4O. So we've lost two hydrogens, we've removed two hydrogens, so it's an oxidation reaction. So for our equation then we can use the O on the left, and that can be used to remove those two hydrogens to give us the water. So that's familiar. Now what we're going to move into then is if we have the aldehyde, we can do a reaction to get the primary alcohol. So we're going in the other direction, and that's reduction. So oxidation and reduction. Reduction then, we need a reducing agent. So this is a new reagent, NaBH4, and the AQ state symbol is important. We'll see why soon in our mechanism. But sodium borohydride is the name. In the exam, you're often asked to state the reagent, in which case it'll be easier for you to just remember the formula, just like you do with the potassium dichromate. So NaBH4 is our reducing agent, and we can represent this with a H in square brackets because reduction is the addition of hydrogen and the removal of oxygen. Okay, so let's play spot the difference again then. So this time we're starting with the aldehyde, so C2H4O. We can reduce that back to the alcohol. So C2H6O, we have added hydrogen, so it's a reduction reaction. We can do an equation using our H, but when you play spot the difference, we've got two more hydrogens that we need, so we're going to have to add 2 moles of the H to make it balance. So our first reaction of carbonyl compounds here then is called reduction. So reduction of carbonyl compounds back to the alcohol. So if you start with an aldehyde, you're going to get a primary alcohol, and if you start with a ketone, you're going to get a secondary alcohol. So the reagents then, we've got this NaBH4, that's our new reagent, it's a reducing agent. And the name there, well, I said sodium borohydride. It's also known as sodium tetrahydroborate 3. Yeah, how good is your memory? You know, I think really they tend to ask you to identify or to state the reagent. So NaBH4 is going to be good enough to remember, I think. But sodium tetrahydroborate or sodium borohydride is the name there as well. And so you would react this, you'd heat it up so it'd be warm in an aqueous solution. So let's have a look at the general equation then. So we use a generic carbonyl compound, so the R groups, so we've got R prime, R double prime, so they can be whatever you want them to be, either the hydrogen or a carbon chain. We're talking here about reduction, so reduction is the addition of hydrogen, and so our equation is going to look like this. We're making the alcohol again. So just as you saw in the previous slide, when you place spot the difference, you have to put back 2 H's. So look at the difference there, the double bond. We've now gone to a single bond between the carbon and the oxygen, so the pi bond has broken. We've put a H onto the oxygen to form the alcohol functional group, and we've got a hydrogen on the carbon as well to make sure it's making 4 bonds. So we needed 2 hydrogens to make it balance. Okay, so I'll just highlight those. So the 2H here, so one's gone here and one's gone there. So it's balanced. It's an addition reaction, yeah, it's an addition. You've not substituted anything. It's going to be a nucleophilic addition reaction. So there's the balanced equation to start with. Let's have some practice then, just writing equations for the reactions before we move on to the mechanism. So equations then for the reduction. So reduction then, we know now, reduction of carbonyls. We need our H in square brackets for our reducing agent, and they are all carbonyls. Look at the names. You're looking at the ending of the name. So if they end in -one, it's a ketone. If they end in -al, it's an aldehyde. So reduction is the addition of hydrogen. We're putting hydrogen on to convert it into an alcohol. So can you work out what the alcohol is going to be each time? And could you do a balanced equation using the H in square brackets, and can you name the product produced? So just press pause and have a go at that, and then press play when you want to check your answers. Right then, let's see how you did. Let's work through them together. Methylbutanone. So it ends in -one, it's a ketone, and so we can see the C double bond O in the middle of the chain, and the methyl group couldn't have gone on any other carbon there. The alcohol then looks like this. So we've changed the C double bond O to an OH, and the name, well, we would start with carbon number 1 here, because that would give us our lowest number for the alcohol, which is the functional group. So it would be butan-2-ol, but don't forget we've got the methyl group, so that would be on carbon number 3, and there it is, 3-methyl-butan-2-ol. So it's a reduction reaction. Let's play spot the difference. The difference is we've added hydrogen, and there they are. We've got 2 there, so we need 2 H's on the left-hand side to balance. Okay, question number 2 then, butan-1,4-dial. So we've got 2 aldehydes, and we're going to convert that back to the alcohol. They can both react, so we go from a dial to a diol, and the name of that molecule then would be butane-1,4-diol. So you can leave that E on, the parent alkane name for a diol, you can leave the E on there. Okay, so again, play spot the difference. So you're looking at an extra hydrogen on the oxygen at both sides, and also on the first and last carbon. So to balance, you actually need 4 hydrogens there. So hopefully that one didn't catch you out. So we had the dial, we needed 4 hydrogens. Okay, last one then, cyclopentanone. So it is a ketone because the C double bond O, that carbon there, has a carbon either side, and it's a cyclopentanone. And so the corresponding alcohol then is going to look like this. Okay, so what would we call that then? Cyclopentanol. So we've changed the "-one" for an "-ol". Now a little bit trickier to visualise because it's in skeletal, but we've definitely got a hydrogen here, and if we could kind of look at that carbon there, we can see the 3 bonds made using the skeletal formula. So there must be a 4th one there, and that's attached to the extra hydrogen that's put on. So again, we need 2 hydrogens to balance. So now we've had some practice writing equations, let's have a look at actually the mechanism for the reaction. So remember, an equation starts with the reactants, finishes with the products. The mechanism shows you step by step how the reactants react with each other to form those products. And remember, the name for the mechanism for this reaction then is nucleophilic addition. So we've got to have a nucleophile. Now the nucleophile is the attacking species at the beginning. We get that from our reducing agent. So the NABH4 provides us with our first hydrogen, and it's in the form of an ion that we call the hydride ion. So remember, a nucleophile can donate a pair of electrons, so that's why we've got that pair of electrons drawn there. But essentially it's a H- ion, which is something we've not seen before. We're familiar with the H+, of course, our proton or hydrogen ion. This is called the hydride ion. So remember, think about chlorine and chloride, so ending in "ide", we've now got this negative ion. Okay, so the nucleophile is our H-. Description of the mechanism then, let's use a carbonyl compound. Let's go with methanal. So it's an aldehyde. Now the story begins with that permanent dipole. So that's the first thing you should draw on, the partially positive carbon, partially negative oxygen. And then our nucleophile is going to come in and it's going to attack that partially positive carbon. And we show that attack by drawing a curly arrow. And remember, the curly arrow shows the movement of a pair of electrons. So we start that arrow at the pair of electrons on the hydride ion, and we finish the arrow on the carbon, because those electrons are going to be used to form a new covalent bond between that carbon and that hydrogen. Now, when that bond forms, that carbon can't have 5 bonds, so a bond has to break. So it's the pi bond between the carbon and the oxygen that's going to break. And so the curly arrow starts at the bond, and both electrons are going to go to the oxygen. So the type of bond fission we've got here is heterolytic. So heterolytic bond fission of that pi bond. Now, if you're asked to describe this mechanism, they're looking for this diagram. But if they did ask you for a worded description, we would say here that the pi bond has broken, not the double bond. Notice the sigma bond isn't breaking, it's just the pi bond. Okay? So that first step of the mechanism involves the dipole and 2 curly arrows. Then we draw what it looks like next. Okay, so we've now got that hydrogen attached. So if I just highlight that one, let's see. There was the hydrogen there. It's now here. Okay, that sigma bond to the oxygen has stayed intact. The 2 hydrogens that were originally on the carbon, we've just moved those to either side. Now look at what's happening to the oxygen. Think about it now. The pi bond has broken. That pi bond consisted of a pair of electrons. One of the electrons was owned by the oxygen. The other one belonged to the carbon. So they've both gone to the oxygen. So oxygen has gained an electron. It's gained the electron that used to belong to the carbon. And that's why we've now written a minus charge here. Okay, so that oxygen, that negative charge is important because the oxygen has gained an electron from that pi bond that's been broken because it used to belong to the carbon. Now this is our intermediate. Okay, so what they'll look for in the exam is that you've drawn that single carbon-oxygen bond and the oxygen has got the negative charge on. Now notice we've drawn a lone pair on the oxygen. That's just to get ready for the next bit, because you can see it's starting to look like the alcohol now, but we do need to put another hydrogen on that oxygen. So if you remember from the balanced equation that you've been doing, we need two hydrogens. We can see that the first one has come from the hydride ion, which was from our reducing agent. Now remember we said the reducing agent, it was important to put the AQ state symbol, and that's because our second hydrogen comes from the water. So we need to draw a water molecule close to that oxygen, and remember the water molecule will have dipoles, so partially positive hydrogens there. So draw it with the partially positive hydrogen close to the oxygen, and hopefully you can predict what's going to happen next. We need to steal a hydrogen from the water, and so the oxygen is going to bond with the H using that lone pair. So we're going to draw another curly arrow going from that lone pair to the hydrogen. Now that hydrogen needs to be released, so the HO bond in the water needs to break. Again, it's heterolytic bond fission, so the arrow goes from the bond and the electrons are going to the oxygen. So then we redraw. We're looking at our products now. So we've got our OH. We've made our alcohol functional group. Don't forget though, we've used water here, so it's important that we also write in our hydroxide ion there. Okay, so our mechanism really is those two steps, and then we've got the product there, which is our alcohol. In the middle step, we've got that H plus or delta H really has been provided by the H2O. Now you will see it in some textbooks provided as a H plus, but the preferred answer here for the reduction reaction is to get that second hydrogen from the water. Here is propan 2-ol. Time now to pause to check your progress using the learning outcomes on the front cover of your notes. This PowerPoint, remember, was all about the reactions of carbonyl compounds. Well, the first reaction that we learnt about was just to do with the aldehyde. It was the oxidation of the aldehyde to form the carboxylic acid. Now, we didn't look at the detail of that reaction in this PowerPoint, but you do know that from previous stuff. So make sure you're happy that you can describe the oxidation of the aldehyde. So you can do a balanced equation. You can state the oxidizing agent and the conditions for that. The new reaction, though, that we've just studied is reduction, and so we have a reducing agent. That's a new one, and that's the sodium borohydride. Now, the mechanism is nucleophilic addition, and it's all about converting the aldehyde back to the primary alcohol or the keto back to the secondary alcohol. So make sure you're confident with those. So you need to be able to describe those reactions. You need to be able to describe the mechanism as well. So if the question asks you to describe the mechanism, that's the story of how it happens, always name it first. So when you answer nucleophilic addition, get that spelling right, nucleophilic addition, and then go into drawing out what's happening with your curly arrows and so on. Okay. Textbook pages then 457 to 459, use those for a little bit of additional reading. There might be some additional questions in there as well. So that brings us to the end of part 1 of the reactions of carbonyl compounds. There is a part 2 because there is another reaction that the carbonyls can do. You'll be pleased to hear, though, it'll follow the same mechanism. Okay, it's just a different reagent. So instead of it being reduction with a reducing agent, we're going to look at something different, but it'll still follow the same mechanism. Okay, but that's in a different PowerPoint. That's in part 2. So for now, we're done with this one. What I have done, though, is left on a couple of slides after this with some basic practice questions just to get you practicing the balanced equations. So I suggest that you stop the video or PowerPoint now, just have a little break, process what you've learnt, and then have a go at those basic practice questions just to finish off for now. Okay, thank you.